Okay, here's a guided walkthrough through the 2009 Physics B question, and this is an experimental question. So these are the types of questions that we really want to try to practice more and more. So here we go. In an experiment, students are to calculate the spring constant K of a vertical spring in a small jumping toy that initially rests on a table. When the spring in the toy is compressed a distance of x from its uncompressed length, so from its equilibrium point, L naught, and the toy is released. The top of the toy rises to a maximum height of h above the point of a maximum compression. The students repeat the process several times, measuring the height with objects of various masses taped to the top of the toy, so that the combined mass of the toy and added objects is m. The bottom of the toy and the spring each have negligible mass compared to the top of the toy and the objects taped to it. So we are only considering the mass of the objects that they're taping to the top here. So if we were to do forces, this could be pretty complicated, but basically this is really easy if we look at energy. Okay, so here's our initial situation, and here's our final situation. Alright, so A, we're looking for derive an expression for the height in terms of the constants mx, k, and fundamental constants. So a fundamental constant would be something like g. Now, when they're kind of giving us all these constants, this should probably remind you to use energy, because I think that this would be pretty familiar to you. So if we look here, the initial energy is just our spring potential energy, and the final energy is gravitational potential energy. So this is 1/2 kx squared is mgh. So if we're looking for h cleans up to kx squared over 2mg. So this fits all of the requirements that they asked of us. They said it had to use m, x, k, and fundamental constant, which is g. So that's very good. So right here at the bottom we can see their data, and this is important information that they tell us that the compression is the same. So unlike the experiment that we did in class, we changed the compression each trial. This time they're only changing the mass. So x is, the compression is a constant. Okay, so we're going to use this data table really for part B. So part B1 and part B2. Now for B1, we want to figure out what we would graph to find the slope of a straight line, so a linear relationship that would be able to use for the spring constant K. So I'm going to basically take our equation that we did in A, and I'm going to solve for K. So let's see what K actually equals. Okay, so rearranging, we get 2mg h over x squared. Okay, now let's identify what is constant, because we don't want to just graph a whole bunch of nonsense. We want to keep this as clean as possible. Okay, 2 is a constant, obviously. G is a constant, and then x squared is going to be a constant because the compression is the same. So the only things that are changing are the mass and the height. Okay, so there's two acceptable solutions here, and it's kind of your choice. Okay, so remember that slope is y over x, so change in y over change in x, right? And if this is 2mgh over x squared, okay, so we're going to have to kind of rearrange this so that one of these is in the top, one of these is in the bottom. So you have two options. You could either keep mass on the y-axis, and plot that versus the inverse of height on the x, or you could plot height on the y versus 1 over mass on the x. Okay, so I'm actually going to recommend the next one, the second one, just because looking at this data here and kind of looking at part 2, it tells us to find these quantities. You can see the inverse of these values are going to be a bit cleaner numbers than the inverse of the heights. So I just figured that would make my graph a little bit easier to plot. So that's going to be the one that I choose, but both are acceptable. Okay, so filling in kind of our table, I'll try to make a quick table here. So we're going to have 1 over mass, then mass, and then the heights. And honestly, I'm not going to take the time really to recopy down the heights. So for the first value, the mass was 0.02 and the height was 0.49. Okay, so just kind of look back there. Let's see. So the inverse of 1 over 0.02, that gets us a nice even number of 50. Okay, the second one is 1 over 0.03. Okay, and that comes out to about 33. 1 over 0.04. That comes out nice to be 25. 1 over 0.05 comes out to 20. So another nice number. And the final one, 1 over 0.06, comes out to about 17. Okay, so this is 0.02, 0.03, 0.04, 0.05, and 0.06. Okay, so this is what they're looking for in part 2. Okay, so on to part C. So now we're just going to have to plot our data. Okay, so now that we know what we're going to graph, I told you I'm going to graph the height on the y-axis, and I'm going to graph the inverse of the mass on the x-axis. Okay, so that's what we're looking at part C. I am, because I do not know how to shrink this picture yet, I'm going to go to a next slide, and we're going to make our plot. So I do enjoy this tool quite a bit. It's a bit easier than actually graphing. Okay, so so when you are graphing, you need to make sure that you do label your axes and your units. I think I'm going to maybe make this a little bit bigger since I have the room. Kind of the bigger it is, the cleaner you can make it. 40. I'll make this a little bit bigger. Okay. Because it is kind of hard for me to write small here. Okay, so remember this is 1 over mass. And my units are inverse kilograms. Okay. So let's see if I have the room here. If it's a little bit stretched out, that's okay. 0.2. So you obviously want to scale, make your scale pretty easy to record your data. Alright, here's our height. So now I'm going to do the boring thing of plotting my data. So let's see, let's go back to the height. So the height for my first point is 0.49, and 1 over m is 50. Okay, so maybe I'm going to use a different color here. I think orange sticks out very well. So here's 50.49 is going to be, about there. Okay, our next point. Okay, we have 1 over m at 33, so that's my x, and my y is 0.34. So 33, then 0.34, and I think that's about there. It is hard for me to be very precise, so you would be able to do this a bit better by actual hand than me. 25 on the x and 28 on the y. So 25, that's easy to find. And we said 28, so it's about there. Oh, it's so hard to make these small dots. No, I don't want to select all. Okay, alright, that's a bit easier. Okay, 20 on the x and 0.19. So 20.19, that's going to be right about there. And finally, we have 17 on the x and 0.18. So 17, let's see, 19. Wow, so those last 2 points are very close. Now, it does say that we want a best fit straight line, so a linear relationship. Let's make sure we follow the instructions. I am going to kind of cheat a little bit with my straight line tool. And let's see what's a good color that will go. I don't know, maybe blue will stand out. Okay, so this is going to be a little challenging for me. Let's see how this goes. Okay. I think this is okay. All right, it's a bit challenging on here, but for the most part, this fits our data pretty well. My point there is kind of a mess, but we'll take this kind of with a grain of salt. For the most part, this is a linear relationship. Okay, and I'll go back to our blank white background. Now D, let's please read instructions. Okay, D says, using your best fit line. Okay, it does not say use a formula that you calculated. Okay, let's please read that carefully. I've seen that missed many times before. Okay, so, slope, change of y over change in x. So we just need to pick 2 points here, right? So y2 minus y1 over x2 minus x1. Alright, let's, my graph may not be the easiest, but let's try to estimate maybe 2 points here. Let's see. Okay, this one seems, this point right there seems pretty good to me. So this is going to be 45 and 0.48, it looks like to me. And let's pick another point. Actually, I think this point too is pretty good. So you want to pick 2 points where it kind of intersects 2 lines, right? You would not want to pick a point that is, here, because it's in between 2 squares. Okay, so you would have to kind of guess. So you want to avoid guessing as much as possible. Okay, so and this one is 35, and it looks like the height is it's actually, I messed up a little bit. This would be 0.46. My apologies. Okay, those are our 2 points, and so let's find what this k value is. So remember, our slope is equal to this. So our y values, our second one is 0.46. So 0.46 minus 0.36 over 45 minus 35. Okay. Oops. Okay, so here is our slope, and this comes out to be 0.01, and actually made a mistake before. This is not k, right? This is just the height versus the inverse of mass, right? So if we look at our units here, this is inverse kilograms, so in the denominator. So our units here are meters times kilograms. Okay, and remember, if we go to our equation for k, I said was 2 mgh, so 2 times the potential energy over x squared. And what we just found out from the slope was essentially this right here equals m times h, right? Meters times kilograms. So essentially, now that we know the slope, then k is going to equal 2 times g times our slope, right? So I'm just kind of write slope for now, times x squared. Okay, and like I said, this is going to go right in there. Okay, so k, so now we have to calculate. K is 2 times 9.8 meters per second squared times 0.01 And the compression that we were, the compression was 0.02 meters. So we need to square that. And this comes out to be 490 Newton meters. Now, there is some variance here because this is largely dependent on your line of best fit. Okay, I warned you that mine wasn't exactly perfect. So the AP guidelines will give you some leeway here, about plus or minus 25% or so from what they perceive as the ideal answer. So they would accept values between 450 and 550. So when you are making this, do not stress out so much about the exact number. What they're really looking for is the process here. Alright, on to the last part, E. And E, we are writing a procedure describing how we would measure the height in an experiment, given that the toy is only momentarily at the maximum height. So basically, we want to write a method that could eliminate human error, essentially, or make it very, very small. So a few, options here. There's not just one solution here, but kind of the first one that comes to my mind would be to tape a meter stick perpendicularly, so that's what that means, to a wall, or something straight. Place the spring toy in front of the meter stick. Now, my next kind of thought here was to set up a slow motion camera. Now, we could also use something like a photo gate to get the velocity. If we got the velocity, then we could use energy conservation to calculate the height using kinematics. But this is kind of the first thing that comes to my mind. And you kind of want to make sure all the details matter here. So on a fixed stand, right? So something that's not going to move, we want to eliminate this error. Let's see, my step 4 would be to film, right? So obviously film the launch of the spring toy. For each mass, and then what are we on, step 5? Okay, then you're going to obviously want to watch the video and identify the maximum height. And they didn't really mention this, but I'm going to say repeat 3 times for each mass for precision. And that's really all it says, because it only asks us to design a procedure that would help identify the maximum height. So it's really not more complicated than that. I hope this helped you guys. This is a good question to look over. Right? These experiment questions can be tricky at times. So I hope this helped. Thanks.